Hello everyone. Today I am going to discuss about Class A power amplifiers. Actually, in the last video, we have given the introduction about the power amplifiers, what are the applications of it, classification of amplifiers and so on. Now coming to the power amplifiers, there are 4 classes. One is Class A, Class B, Class AB and Class C. So in this video, I am covering Class A, its operation, its 2 varieties and the derivation of conversion efficiency. The contents covered in this one, from the continuation of the previous video, now I have to tell about the principle of power amplifier first, then it comes to Class A, Class B, Class AB and Class C. The first power amplifier, Class A amplifier, I am going to discuss about the complete details and the derivation part of it also. Coming to the principle of power amplifiers, if I take the power amplifier circuit, it contains basically 2 parts. One is the transistor part. So this I am dividing into 2 parts. One is the transistor part, DC power supply and the load. If you look at this diagram, so here the 2 arrows indicating first from the DC source, we have to convert this DC source into AC source. So the power consumption is the main criteria here to divide different classes of amplifiers along with the operating point. Suppose if you look at this one, the main power transistor, if I consider it as a person who is basic responsible for this conversion, and whatever the converted load, it has to be shared to the load. So maybe if I take, this is the head of the some home, some parent, and the total income I am considering as the DC power, and the power delivered to the load, I am calling it as a power given to the children or the expenses given to the money given to the children. So here the basic principle is, whenever I am providing some DC power, the basic principle of power amplifier, it should convert this DC power into power DC into AC power or the power delivered to the load. So the main power should be divided into 2 powers. One is power consumed by the basic transistor and power, the remaining power delivered to the children or to the load. Suppose if the main operating transistor or the person who is doing all these functions, if they themselves consume more power, then the remaining power delivered to the load should be or will be going to be less. So here the one principle is the total DC power, it should be maximum power should be delivered to the load and the power consumed by the transistor should be less. So this principle, if we work out, the efficiency is going to be increased. So before going to this one, the efficiency of the power transistors, basically it is defined as for a given DC power, how much it is delivered to the AC power, that is to the load. If PAC is more when a given PDC, then efficiency is going to be increased. That is indicated in this diagram. That is the conduction of transistor which is responsible, okay, it is less, then the remaining rest power or leftover power, it should be the more which is delivered to the load. That is, if the consumption is less, power delivered to the load, then efficiency is going to be increased, conversion efficiency. So this is a basic principle behind all the classes of power amplifiers. So in Class A, what is happening? The transistor is going to conduct for a longer time. So that's why more power is consumed by this transistor and less power is delivered to the load. That's why conversion efficiency will be less. For the remaining transistor, this scenario is going to be altered such that the power consumed by the transistor is maintained as less by maintaining its conduction period less, and the leftover energy will be transferred to the load. So that's why the efficiency is going to be increased. So that's why the from Class A to Class B. So suppose first if I take the Class A, then here the transistor will be conducting all the time. throughout its cycle, 360 degrees. Then when coming to the class B, it is reduced to half the amount. That is, half the time it is not working, so the power consumption is eliminated for half of the time. That reserved power will be transferred to the load. Then in the class AB, it is in between. Transistor conducts between 180 degrees to 360 degrees, so that the remaining power will be transferred to the load. So it is more than the class A efficiency and less than the class B efficiency. So in class C, less than 180 degrees, that is gradually the reducing the amount of conduction time by the main transistor, so that we are reserving some power. That reserved power is going to be delivered to the load, so that conversion efficiency is going to be improved. So we will see the operation of class A and how the conversion efficiency is derived. These two parts I am going to be covered. So maybe this we can visit all the classification or comparison of all the power transistors. Only the point which is needed I am going to consider here. If you look at here, the basic 2 points, the remaining points at the end of the all the 3 sessions, we are going to compare once again. If you look at here, first difference is Q point or operating point for a class A power amplifiers. It should be in the middle of the load line, that is in the active region. Then for class B, it is on the cutoff, and class AB between cutoff and active region. For class C, it is below cutoff, and angle of conduction, it is 360 degrees by the transistor, and for the class B it is 180, class AB between 180 and 360, class C is less than 180 degrees. And the same thing is indicated in the region wise, active, and it should be active and cutoff, it should be on the cutoff, it should be between cutoff and active, and it should be below cutoff. So what is the basic difference when you come to the operation? The input and output are going to be same. It is known as faithful reproduction. But in all other amplifiers, the output is not going to be the same as the input. So let us see the waveforms. If you look at the waveforms before going to the operation, this is the output of class A when an input is provided as this AC signal. If you look at the class AB output, so this portion is not going to be allowed. That is going to be the portion which is eliminated. So the remaining all this portion is going to be appeared at the output. For class C, only this portion is going to be appeared at the output. For class AB, for class C, only the small amount of power, okay, all the remaining shaded area, so which is not going to appear. So it is the non-conduction area. So if you look at only in class A, input and output are resembling the same, and in all other cases, the output and input are not going to be the same. So there are 2 types of class A power amplifiers. One is series fed, which is load is connected directly in series with the transistor. That is the first class. The second one is, instead of directly connecting the load, it is connected through a transformer. So if you look at the input and output waveforms, the input and output are resembling the same, and I'll explain the operation. Suppose if any signal is given as Vs at the input, and VCC is the DC voltage we are applying. This DC voltage provides some current IC which is flowing through this one, and the transistor conducts for all the time 180 degrees time. That's why for positive half cycle, negative half cycle, input is produced at the output. So this operation of class A amplifier or class B or class C will be explained taking its load line. So how the load line is drawn? First we have to take the DC line. So I'm drawing the from the circuit, okay, output equation. So output equation will be, loop equation will be VCC is equal to ICRC plus VCE. This is the VCE. So from this, so what is going to be IC is equal to VCC minus VCE divided by RC. Or if you write in terms of equation, Okay, next line I am going to write. So output loop equation will be VCC is equal to ICRC plus VCE. So I require load line I have to draw. I am drawing once again VCE versus IC, which is a output and output characteristics of transistor. It goes like this. So now we have to note it, what is the active region, what is the saturation region, and what is the cutoff region. So from this equation I am writing IC is equal to VCC minus VCE divided by RC. So this is equation of line, okay, where, so this is the DC load line, because we are considering only the DC conditions. Okay, this is Y is equal to mx plus c in this form, circuit equation. So where this is the c and this is mx. So y axis is x axis is VCE, y axis is IC. So in this one the load slope is 1 minus 1 by RC. Okay, concept this C value is VCC by RC. So finally I am pointing out this is VCC by RC. So this final point is VCC, and the portion here it is active portion, and this point we call it as cutoff. This point we are calling it as saturation. So now as we have told, this class A amplifier will works in active region, that is Q point selected should be on this one. So I am selecting in the middle of load line. So this is the Q point, which is VCE versus IC. So here Q point I am noting as VCEQ, ICEQ. So from this we have to derive what is the DC power and AC power. So we'll see once again this one. So this is the Q point, where the Q point is, this is on x axis VCE, on y axis ICQ. Because we require, for deriving the efficiency, we require DC power as well as AC power. Now on this load line I am providing this signal, a sinusoidal signal, because on this Q point, DC point, we have to superimpose this AC signal. And if you take this one and project on the output line based on this load line, so this will appear as IC. So it is containing IC maximum, IC minimum, VC maximum, VC minimum. So from this we have to derive the different parameters. So here I will write first what is the DC power. PDC is equal to ICQ into VCEQ. So at DC level, what is your operating point? VCEQ and ICQ. So VCEQ into ICEQ will be your power. So there will not be no change in this DC power. Next we have to take the AC power. So for this AC power we require VRMS AC value into IRMS, because we require this load line, that's why I am keeping the same slide. Now you can see what is the peak to peak value for this V. Okay, so VRMS, first I am taking the V maximum, or V peak to peak is equal to, first V peak to peak is equal to V CE maximum, V maximum. Okay, so we'll write on the different slide. Okay, so PDC I will keep it aside as ICQ into VCQ. Okay, next PAC is equal to, we have to take it as VRMS into IRMS. First we will consider V peak to peak. So from this V peak to peak is V maximum minus V minimum, that is the peak to peak. So V max minus V minimum is peak to peak. So I require only maximum value, that is on one side, one portion. So it is a symmetrical value. We have to consider it as, from this I am considering the V maximum as V max minus V minimum. That is, one peak is V max, another peak is V minimum divided by 2. On similar grounds, here you can see on ICQ, your IC maximum and IC minimum is produced from the output equation, which is VCC is equal to ICRC plus VCE, or IC is equal to VCC minus VCE by ICRC. So from this, now I peak to peak I can write as, on similar grounds, I maximum minus I minimum. I minimum is the I peak to peak. So from this, I maximum is IM, that is one side, I max minus I minimum divided by 2. Now I want RMS value. We know that VRMS is equal to VM by root 2 and IRMS is equal to IM by root 2. Then from this, what is VRMS? V max minus V min divided by 2 root 2. And from this next equation, IRMS is equal to I max minus I minimum divided by root 2, 2 root 2. Now I am considering PAC. PAC is equal to VRMS into IRMS. So what I can write, it is V max minus V minimum into I max minus I minimum divided by I max minus I minimum divided by 2 root 2 into 2 root 2. It becomes 8. Now this is the PAC. Now I am coming to the conversion efficiency, which is known as PAC divided by PDC. So it is V max minus V minimum into I max minus I minimum divided by 8 into VCEQ into ICQ. So this is our conversion efficiency. Now I am coming back to here, load line. So the conversion efficiency, for maximum values we have to consider. Suppose if you take this swing, what is the maximum swing it can go up to? It can go up to, I will show you in a different color. So the maximum swing it can go up to this value, like this, here up to this. So now we have to define what is V minimum, V maximum. So minimum value it can go up to maximum levels. So V minimum, minimum of minimum it can go up to 0. V maximum it can go up to VCC level. So it is VCC. Now if you look at here, so what is the maximum swing it can go? It can go up to here, and here also it can go up to here. So on ICQ, it is going to maximum extent of VCC by RC, and here it is minimum extent of 0. So from here I can derive I minimum. IC minimum is, minimum of minimum value is 0. IC maximum value. So it can be the remaining portion, it is maximum one more ICQ. So it is 2 ICQ. To derive the maximum efficiency for class A series fed amplifier, so these are the values. Now I am substituting in the formula, which we have this one. So here I am directly substituting. V maximum is VCC, V minimum is 0, okay, minus 0, and it should be I maximum 2 ICQ and I minimum is 0 divided by 8 ICQ into VCEQ. So if you take this one, this maximum value of VCEQ is from here. What is the maximum value of VCEQ is? It is VCC. So instead of VCEQ, I am just putting it is VCC. So ICQ, instead of VCEQ, VCC. ICQ, ICU gets cancelled, VCC gets cancelled, it becomes 2 by 8, that is 1 by 4. So it becomes into 100%. Efficiency is expressed in terms of percentage. So conversion efficiency for series fed, it is 25%. So I'll show you this here as a series of this one. Efficiency is PAC by PDC into 100%. V peak to peak, V maximum by V minimum. VM is V maximum by V minimum by 2. IM is I maximum by I minimum by 2. From this we are calculating VRMS and IRMS, substituting in PDC, and conversion efficiency is PAC by PDC. So this is the formula we are going to get V max minus V min by I max minus I min by 8 VCC into ICQ. Now I am substituting these values. What is V max, V minimum, I max, I minimum from the load line for taking the maximum excursions it can take, the input signal and produced as VCQ and ICQ. So from this one, if you substitute all these values, so here VCC, maximum value will be VCC. So I'm substituting here VCC, VCC into ICQ, so it becoming 25%. So why this 25% only efficiency means, if you take this circuit diagram, because all the time transistor is operating, so some load is, some DC power is consumed by this one, only the remaining portion of the power is delivered to the load. Suppose instead of directly coupled this load, it is known as series fed. Load is fed to the in series with the collector. If it is separated from this one, so we can increase the conversion efficiency. So we have modified the circuit, by this one. So instead of, this is a normal load, instead of connecting like this, through a transformer, a load is connected to the circuit, to the transistor, so it is isolated from the load, and it consumes, that is, it is isolated whenever this transformer is reflected onto the primary side. So it becomes, RL becomes, because this primary transistor, primary resistance, the resistance of primary, normally the resistance of the primary transformer will be very, very less. So it is approximately taken as a 0. So because the load is 0, now if you write the output loop equation for this one, so here what is the total resistance? So VCC, now it is nothing but ICRC. Same equation I am writing once again, plus VCE. So this IC means primary transistor, it becomes 0. Now VCC becomes VCE. So now VCEQ becomes VCC. So previously it is laid on the VCQ, now it is laid on the VCC. Now you can see the load line, this point is transferred to the VCC instead of VCQ. So whenever you are applying a signal like this, it is reflected onto the load line. Still here the same Q point is maintained in the active region only. It is middle of the load line. Now the equations, everything will be the same. The previous equation will be whatever the equations we are showing here. So this will be hold the same thing, but except these maximum excursions, V max, V minimum, I max, I minimum are going to be changed. How these are going to be changed? Based on the load line. So here you can see from the VCC, it is having a maximum excursion on the cutoff point. So from VCC to another VCC, so this maximum point becomes, V max becomes 2 VCC. And V minimum as usual it is 0. I maximum is 2 ICQ, it is same as the previous one, and I minimum is 0. Now we will substitute all these equations in the conversion efficiency. PAC by PDC, V max minus V min into I max minus I min. So if you substitute here 2 VCC into 2 ICQ by 8 VCC into ICQ. So now if you cancel out this VCC, ICQ, it becomes 4 by 8. 4 by 8 into 100 becomes 50%. So from previous 25%, if it is connected load is directly to the output of the transformer. Now it is taken through a transformer, then it is increased to 50%. So in class A, there are two types. As a conclusion, I can tell you, in class A series fed power amplifier, the conversion efficiency is 25%. If you take the same circuit diagram, same operating point, only the changes we have made is the load is taken through a transformer so that it is reflected onto the primary, and it is become, you can see the load line. So it is infinity means RL is 0, 1 by 0, it is infinity. That's why the slope becomes infinity, load line becomes vertical. And the excursions will be, only this excursion is going to be changed from simple VCC to twice VCC. So that's why 50% of efficiency, DC power is converted into AC power. As I have told in the first principle, what is the principle of operation? Here transistor is, instead of 360 degrees, it is having the same 360 degrees, but the load which you are connected, because we have decreased the load resistance from normal load to 0. So because of this, the power has been reduced. But from this, in class B, we are going to reduce to 180 degrees, and so that this efficiency still is going to be increased, kind of thing. So all these things, operation of class B, its derivation of power efficiency, load line and everything. Coming to the input and output waveforms. So because it is conducted throughout the 360 degrees, input is resembling the output. That's why no distortion is observed in the class A power amplifier. So as a conclusion, Q point of class A amplifier is in the active region and the middle of the load line, and obtained for the full cycle. That's why output is faithfully reproduced, that is no distortion is available, and for the complete input cycle the output is obtained, and the power efficiency is 25% to 50%. So the efficiency is going to be in for class A 25 to 50%. Then by just altering the conduction angle, we are going to increase this class B efficiency to the remaining 78.5% and 50 to 78.5, and class C 90, approximately 90%, and so on. So I am going to discuss this in the part 2 for class B power amplifier operation and its derivation in the next session. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.